Here's an introduction to vector line integrals. Again, with a applications feel to it right off the bat. There's really two cases. There's two models for common models for vector fields that are really helpful. One is the flow of a fluid, and so that the vectors are the velocities of the particles of the fluid. And then there's also a force field, something that permeates space and makes you move, like gravity or electric field or something like that. And they're both useful, and they both lead to vector line integrals. So here's the situation. Suppose I've got this vector field. Let's say it's y comma x squared, or in the other notation, yi plus x squared j. And I've got a circle centered at the origin with radius 2, somewhat like, I'm going to do the whole circle because it's maybe more interesting, it leads to more interesting stuff later, as opposed to the scalar line integral situation. And I'm going to go around it. It's going to be very important that we have to tell which way to go around. You'll see in a minute why that's important. And what I'm going to do is I'm going to take the vector line integral of this function on this curve. What would that mean in these two situations? Well, the force field is a little bit more direct as long as you know some physics. This vector line integral, I'll show you the notation in a minute. The vector line integral of a force field, I claim, is calculating the work. So let's see. Let's just go back to our understanding of work. Let's suppose, well, let me show you a nice picture for a second. We'll come back to it. But let me just give you, here's a picture of this vector field. And I'm going to show you, I'm going to put in the curve, I'm going to put in the circle. Oh, that's not going to work. Okay. So it's about like that. Okay, that's roughly the right circle. And here's the arrows of the vector field. Here's the circle. What I'm going to do is I'm going to go around the circle counterclockwise. And how would the work, as it were? Well, at any point on the circle, if I go a tiny distance along the circle, I'm basically going along a straight line. And I'm going to have work, I'm going to have positive work done on me if those force arrows are generally in the same direction. If the dot product of the force arrow and my velocity vector going this way is positive. I'm going to get zero work if they're perpendicular. Like here I'm going this way and the arrows are going this way. And I'm going to get negative work if as I go counterclockwise the arrows are going opposite me. So we know that for a straight line, the work formula, let me go back to let me just put in a few of those arrows. They were kind of going with me here, perpendicular here, and opposite here. We know that the work formula for a small segment, if I'm going on a little segment like this, and the work vector is like this, or the force vector is like this, let's see, I need a notation for this guy. A good notation for this guy will be, I usually have r of t being my curve, my explicit parameterized curve, so it's going to be a little bit of vector motion along the curve. I'm going to call it dr with a vector. It's very important that this is not just ds, which is the scalar length. This incorporates the actual displacement along a tiny bit of the curve. Okay, so a tiny bit of work, basically this is supposed to be a blow up of a little bit of the curve here. This little bit here blows up to dr. The small amount of work that we do along that segment, we just use the usual linear formula for work, which is f, I'll even color code it, f dot dr. So at any point on the curve, I look at how far I went and what direction for a tiny little bit of time. I look at the dot product of that with the force vector, and I get the work, the small amount of work that's being done on me by the force in that little bit of time, and then I'm just going to integrate it. And so that's going to be the total work. And so I get what's called a vector line integral. Okay. Now we're going to have to figure out how to exactly calculate that. Okay. Well, as with the ds, the main thing is how do you translate this into a parameterization? Okay. Well, if the clock runs for time dt, And I want to know how far and in what direction I went. The displacement vector, well, displacement is just the velocity times the time. This is the vector version of ds is speed times dt. And of course, we can make that a little more explicit. That's r prime of t dt. Okay, so this is going to be explicitly the force vector field dotted with r prime of t dt. Okay, and that's something we know how to do. That's an ordinary one variable integral. It's going to be whatever the limits are. Okay, so let's look at what we have here. Okay, we need the parameterization for a circle of radius 2 centered at the origin. This will work. And we need the time limits. I'm going to go around the whole circle this time, 0 to 2 pi. Okay, and so our r vector is just 2 cosine t, 2 sine t. Our velocity is, now I really do have to pay careful attention to the signs here, and the whole vector is going to come in. Okay, and then f, remember, of xy was equal to y comma x squared. Now that's going to be 2 sine t. I just translate everything into t's, 4 cosine squared t. And I'm going to take the dot product. Oh, this is our prime. I forgot the prime here. That's the derivative. I'm just going to take the dot product of those guys. That's what this is saying. That'll give me an explicit function of t. And that just keeps track of the rate of work, basically the energy flow, as we go, and then we integrate that in dt to get the total energy flow or the total work. Okay, let's see if I can squeeze it. I'll just put it up here. Okay, so the total work is the integral from 0 to 2 pi then of the dot product of these guys. Okay, what are we going to get? We're going to get minus 4 sine squared t, and then plus 8 cosine cubed t dt. And that's a one variable integral that we know how to do. You have to use power reduction here, you have to use a little bit of clever stuff here, but that's a BC Calc integral we know how to do. I'm going to save time, I'm not going to actually do it out, but what do we expect from the picture? We can look at what we expect. I think, yeah, it erased my circle for some reason. Looks like we're spending a lot of time going against this vector field and only a little time going with it. Probably this whole vector line integral around this closed curve is going to be negative. And in fact, that's called the circulation. And the vector field analyzer here is calculating that for us and says, yeah, it's pretty strongly negative. That word circulation is important for the other model of vector fields. Let me say something about that briefly. We could have envisioned this as the flow of a fluid instead of a force field. In that case, what is this measuring? Well, it's a little harder to say than just the word work when it's a force field. But we're basically measuring, if we go along this track, is this vector field circulating in this direction? Is it going overall counterclockwise? Is it flowing overall clockwise? On average, what way is it flowing around the track? One way I think about it is kind of put a little tube in here with mesh sides, so the vector field can flow across it or along it as it desires, and then sort of keep track of, is this vector field just by its nature actually basically flowing around the track or more across it? Well, more often than not, it's flowing around the track, but in the clockwise direction than in the counterclockwise direction. Turns out that that idea of circulation, the integral of a vector field along a closed curve, like in this example, it has a lot of properties that other vector line integrals don't have. And even when it is a force field, even when it is a work calculation, it actually has some very, very, very important relevance to some big theorems that we're going to get to.